The LaunchPad LP-MSPM0G3519 development kit is an easy-to-use evaluation module based on the MSPM0G3519. It contains everything needed to start developing on the MSPM0G3519 M0 plus MCU. The board includes 3 buttons, 2 LEDs, one of which is an RGB LED, and over 80 pins. Analog measurements are enhanced thanks to optimally placed ADC and DAC low-pass filters. The MSPM0G3519 is a 32-bit ARM Cortex-M0 plus CPU with dual bank flash and advanced security features, running at up to 80 MHz. The device can be used in a variety of applications, even with a 100-pin I/O expander, offering dual CAN interfaces, Flash ECC and SRAM ECC. The easiest way to get started with the MSPM0G3519 is by using the LP-MSPM0G3519 LaunchPad shown in the video. It features 512 kilobytes of dual bank flash, 128 kilobytes of SRAM and 16 kilobytes of data flash memory. The device also includes internal analog components such as 2 ADCs, a voltage reference, a buffered 12-bit DAC, and 3 comparators with an 8-bit reference DAC. Rapid prototyping is simplified by the 80-pin headers, which support a wide range of booster pack plug-in modules. Users can quickly add wireless connectivity, graphical displays, environmental sensors, and much more. First, you need to download and install a development environment. The official one is Code Composer Studio CCS, currently available at ti.com. Click on the download options and select the correct operating system. Start the development environment and create a new project. The software will ask for the device connected to the USB port, type 3519 to quickly find the correct device. You can see the board name and the MCU mounted on it. Select LP-MSPM0G3519 LaunchPad, then choose No RTOS as the kernel and the CSS TI ARM Clang compiler as the compiler. You can then create a new project or choose from one of the many examples available in the development environment. After selecting the correct device, the system displays some features of the microcontroller, including the available and used I/O ports. The first example we'll try verifies the operation of the onboard RGB LED. Write the following source code in the editor and compile it by selecting Flash Project from the Run menu. After a few moments, the RGB LED will display different colors. The operation of the algorithm is quite simple. The LEDs change state in a single operation. It could be written in a more readable way at the cost of a longer code. The LaunchPad LP-MSPM0G3519 development kit includes 2 very useful LEDs for quickly testing firmware functionality, a standard red LED and, more importantly, an RGB LED. The RGB LED model is 19-337/R6 GHBHC-A 01/2T and consists of 3 internal LED diodes. They can be connected via the corresponding jumpers J19, J20 and J21 on the board. Specifically, J19 connects PB22 to the blue channel, J20 connects PB26 to the red channel, and J21 connects PB27 to the green channel of the RGB LED. The following example lights up the three internal LEDs in sequence, but since they are enclosed in a single package, the effect is a cyclic change of the three primary colors. The source code is very self-explanatory. The next example is very useful and interesting as it demonstrates generating a sinusoidal signal using PWM techniques starting from digital signals. The resulting waveform could serve as the foundation for more complex systems. Let's set up the following simple electrical connections. Create a low-pass filter with a 1000 ohm resistor and a 3.3 microfarad electrolytic capacitor. The PWM signal is taken from PB22, while the filtered signal goes to the oscilloscope. This is the resulting wiring. The code is quite simple but requires careful precision. The sine wave has been divided into 20 parts, each with a specific duty cycle value. To avoid burdening the MCQ, the 20 values are stored in an array. To achieve greater waveform accuracy, you can increase the number of samples. As seen in the working prototype, the system generates a sinusoidal signal at a frequency of 50 Hz, as specified in the project. The waveform is very good, but it only exists thanks to the RC filter, since the MCU is not generating a true sine wave but rather digital signals. If we remove the RC filter from the circuit, the sine wave disappears and the true digital signal from the MCU is displayed. It's a sequence of widening and narrowing on-state pulses, precisely what gives the power effect to the connected load.